Hello students, how are you all? Welcome to our channel of Beyond Infinity. So in this video we are going to solve the miscellaneous exercise of complex number. By solving the miscellaneous exercise, you will get an idea how to implement whatever concept we have studied in this chapter, and you will get an idea how to approach towards the question that may seems to you difficult, but once you start solving it will be an easy way. We will get an easy way, or you can say that we will know how to approach the questions and finally get to our result. So let's start the exercise. So let's start with the first question. The first question says we have to evaluate this expression. So before solving this expression, we are seeing that it is in the power of I is something in the power. So what basic concept we are going to apply here is, we know that I is equal to under root minus 1. So I square is equal to minus 1. I cube can be written as I into I square. So it will be minus I, because I square is minus 1, and I to the power 4 can be written as I square into I square. So it's going to be minus 1 into minus 1, that is plus 1. So now we have I to the power 18. So we can write it as I to the power 4 whole to the power 4 into I square. And then we have 1 by I whole to the power 25. So when 25 will come inside the bracket, we are going to get 1 to the power 25, which is 1, and I to the power 25. So I to the power 25 can be written as I to the power 4 whole to the power 6 into I. Why we have written all this in the form of I to the power 4? Because we are trying to get everything in I to the power 4, because we know that I to the power 4 is 1. So now what you are going to get, here we are getting I square, and plus here in the denominator we have 1 by I. So you can see that I is in the denominator. We always want I in the numerator part. So what we are going to do, I square, we know that I square is equal to minus 1 plus. Now in the second term we have 1 by I. So as we want I in the numerator, we can multiply both the numerator and denominator by I cube. Here I am multiplying by I cube because we know that I to the power 4 is 1. So in the numerator we are going to get I cube whole to the power 3. So now this comes as minus 1. I cube is nothing but minus I whole to the power 3. So if we are going to take minus 1 common, we are left with 1 plus I. And we know that minus 1 to the power 3 is minus 1, and 1 plus I whole to the power 3. The formula of a plus b whole cube. What is the formula? It is as a plus b whole cube is equal to a cube plus b cube plus 3ab a plus b. So you can remember it as this. And now when we will split this term, we are going to have a cube plus b cube plus 3a square b, 3a square b plus 3ab square. So this is the thing in our question. So we can write it as minus 1. Then in the bracket we will write all these things. A cube. A we have 1. So it will be 1 whole to the power 3 plus I cube plus 3 a square. A square is here 1 only. A square b plus 3 ab square. So a we have 1 and into I square. So now what we have, minus 1 is common, and then 1 raised to the power 3 is going to be 1 only. I cube is minus I plus 3I, and here we are seeing that I square is equal to minus 1, so 3 into minus 1 will be minus 3. So we are having minus 1 common, then 1 minus 3 is equal to minus 2, and minus I plus 3I, it's going to be plus 2I. So now what we will have, minus 1 into minus 2 will be what, 2, and minus 1 into plus 2I is going to be minus 2I. So this is our desired result. So this is our final result. It is in the form of x plus iy. So let's move to the second question. The second question says, for any two complex numbers z1 and z2, prove that real part of z1 z2 is equal to real part of z1 into real part of z2 minus imaginary part of z1 into imaginary part of z2. We know that we can express any complex number in the form of x plus iy. So let's say z is a complex number, then it can be written as z is equal to x plus iy. So we can write z1 as x1 plus I y1 and z2 as x2 plus I y2, z2 as x2 plus I y2. Now what we are going to do, we have to prove that real part of z1 z2 is equal to this. So firstly we will multiply z1 into z2, then see what we are having. So z1 into z2, we are going to substitute this value. Z1 we have z1, so z1 we have x1 plus I y1, x1 plus I y1, and z2 we have x2 plus I y2, x2 plus I y2. So we will multiply x1 by whole this thing, so it will be x1, so it will be x1 into x2, now we will have I x1 y2, then I x2 y1, and then I square y1 y2. So we will have x1 x2, and here we are having, when we will take I common, we are going to have x1 y2 plus x2 y1, and here it is I square, so I square we know the value, it is minus 1, so we will have y1 y2. So we can say that in the real part what we have, x1 x2 minus y1 y2, and in the imaginary part we are having x1 y2 plus x2 y1. So now we have multiplied z1 into z2, so it is saying that real part of z1 z2. So what will be the real part here? If we are going to solve the real part of z1 z2, we are having here as x1 into x2 minus y1 into y2. So whatever we have written earlier, x1 is what? x1 is the real part of z1 and x2 is the real part of z2. Similarly, y1 is the imaginary part of z1 and y2 is the imaginary part of z2. So again we can write it as real part of z1 z2. In place of x1 we can write the real part of z1, because x1 is the real part of z1 and x2 is the real part of z2. minus y1 is the imaginary part of z1 and y2 is the imaginary part of z2. So this is the final result which we had to prove. So we will prove final result. We have proved whatever the question is asking. I hope this is very much clear. Whatever we have done, just we know that z can be expressed in the form of x plus iy, where x and y are real numbers and x is the real part of z, and where x is the real part of z and y is the imaginary part of z. So we have written z1 is equal to x1 plus iy1 and z2 as x2 plus iy2. Then simply we have did the product and then we are getting this result. So let's move to the third question. In the third question it is saying reduce 1 by 1 minus 4i minus 2 by 1 plus I into 3 minus 4i divided by 5 plus I into standard form. By standard form, we mean that it can be in the form of x plus iy. Imaginary part will appear in the numerator. So how we are going to solve this? Firstly, we have 1 upon 1 minus 4i. So 1 upon 1 minus 4i. When we will solve this, let first write whatever it is given, 1 minus 4i minus 2 upon 1 plus I bracket, then 3 minus 4i upon 5 plus I. So here 1 minus 4i upon 1 minus 4i into 1 plus I, we are going to do it as this. Whatever we do in the simple questions also, simple questions, same we have to do in the complex number also. So in the denominator we will have 1 minus 4i into 1 plus I, and in the numerator we are going to have 1 plus I minus 2 and 1 minus 4i will be in the numerator. This whole is multiplied by 3 minus 4i upon 5 plus I. So 1 plus I, we are leaving it as this only. Minus 2 into 1 is going to be minus 2 and minus 2 into minus 4i. So it will be plus 8i, and in the denominator we will have, here we are seeing multiplied by 1 plus I. So we are going to have 1 plus I, and now minus 4i will be multiplied by this. Minus 4i into 1, we are going to have minus 4i, minus 4i into I. So we will have minus 4i square. Then outside the bracket we have 3 minus 4i upon 5 plus I. So now we are having 1 plus I minus 2. So 1 minus 2 is minus 1 plus I plus 8i. So we will have plus 9i, and in the denominator we have 1 plus I minus 4i minus 4i square. So we can write it as 1 I minus 4i is minus 3i, and minus 4i square can be written as plus 4 because I square is minus 1. Three minus 4i upon 5 plus I. So here we are getting minus 1 plus 9i divided by 5 minus 3i. Into 3 minus 4i upon 5 plus I. So again we can multiply this. This question only we have to write in the standard form, so we are doing this. In the easy calc, this question we have to solve in the standard form, so we are doing this until we get in the form of x plus iy. So we are solving it as this. Minus 1 plus 9i into 3 minus 4i divided by 5 minus 3i into 5 plus I. So when we will multiply minus 1 by this, we will have minus 3 minus 1 into minus 4i. So we will have plus 4i, 9 into 3, 27i, minus 9 for the 36, so minus 36i square. And in the denominator we will have 5 into 5 plus I, that is 25 plus 5i minus 3i into 5, so minus 15i into minus 3i square. So we know that I square is equal to minus 1, so we can write here as minus 3 plus 36, because minus 36 into minus 1 will be plus 36, and 27i plus 4i, so it is going to be plus 31i, and in the denominator we have 25 minus 3i squared, so it will be plus 3. So we will firstly write it as 25 plus 3, then 5i minus 15i, we will have minus 10i. So we are having minus 3 plus 36, so 33 plus 31i, and in the denominator we have 25 plus 3, that is 28 minus 10i. So now what we are going to do, we are seeing that I is in the denominator, but we want I only in the numerator. So we will multiply the denominator by the conjugate of this. So we know that the conjugate of 28 minus 10i is 28 plus 10i. Just we have to substitute minus I by plus I. So we can say that here we can again multiply both the numerator and denominator by 28 plus 10i. 33 plus 31i into 28 plus 10i, and that in the denominator 28 minus 10i into 28 plus 10i. So let us draw a line here. We can write as 33 into 28 plus 10i plus 31i into 28 plus 10i. Upon here it is a plus here it is a minus b into a plus b, so we will have a square minus b square, so 28 whole square minus 10i whole square. So now multiplying this 33 into 28. 33 into 28 we are having as 924. 33 into 10i will be 330i. 31i into 28. 31i into 28. 868. So we will have 868i. And 31i into 10i. We will have 310i square. And in the denominator we have to calculate the square of 28. So it will be 784. And here 10 square is 100 and I square. Now we are having 924. And here we know that I square is minus 1. So we will have minus 310 plus 330i plus 868i. 330 plus 868. We have 1198. 1198i. And here we are having 784 plus 100 because I square is minus 1. So in the numerator we are having 614 plus 1198i upon 884. So we are getting this. So we can write it here as 614 upon 884 plus 1198 I upon 884. So it is now expressed in the form of x plus iy. So this is going to be our right answer. So only in this question the main thing is that you have to solve this question until and unless you get in the form of x plus iy. So whatever calculation we have done, we have to do it minutely so that we don't have any mistake. So moving to our fourth question is, if x minus iy is equal to under root this, prove that x square plus y square whole square is going to be a square plus b square. If x minus iy is equal to this, then prove that x square plus y square whole square is this. So this thing is given, x plus iy is equal to under root of a minus ib upon c minus id. So x plus iy, we have under root of a minus ib upon c minus id. So if we have to get the conjugate of this, we will have x minus iy. So simply we will replace minus I by plus I. A plus ib upon c plus id. So this is our equation 1. So this is our equation 1 and this is our equation 2. Now we can do the multiplication of equation 1 into equation 2. Why I am doing the multiplication? Because we can see that here an expression is x square plus y square, and we can say that when we will multiply x plus iy by x minus iy, we will have x square plus y square. So we are multiplying this. So equation 1 into equation 2, we have x plus iy into x minus iy is equal to under root of a minus ib into a plus ib divided by c minus id into c plus id. So here we are going to get x square minus y square. So here we are going to get x square minus iy whole square, and here we are having a plus ib into a minus ib. So we will have a square minus b square. So a square minus b square is here ib. So I square b square we can write it as this, and in the denominator also it is in the form of a minus ib into a plus ib. So we will have a square, that is c square, minus I square d square. So now we know that I square is minus 1. So simple as iy square. So we will have x square minus iy square. So we can write it as I square y square is equal to a square. We know that I square is minus 1. So we will get plus b square, and in the denominator we are getting c square plus d square, because I square is minus 1. So minus 1 into minus 1 will be plus 1. So we are getting x square plus y square is equal to under root of a square plus b square divided by c square plus d square. So you can arriving to whatever we have to prove. So now we are seeing that it is in the under root form. So we can see that whatever we have to prove, we are getting this only. So now what we are going to do, we are going to do the square of the LHS in right hand side and the left hand side, because it is written x square plus y square whole square. So we can write squaring both the sides. So squaring both the sides, we have x square plus y square whole square is equal to, we'll have here under root this into under root this. So we are going to have a square plus b square upon c square plus d square. So this was the thing that we had to prove. So this we have proved. In this question what we have done, we can see that x minus iy, this thing is given. Then as we are seeing that we have to prove x plus as we are seeing that we have to prove x square plus y square. So by multiplying this by conjugate, we can get x square plus y square. So we have taken the conjugate of x plus iy, so we are having x minus iy, and then as we have to get x square plus y square, so we have multiplied this equation, and hence we have got this result. So once you will solve this question 2-3 times, it will be very much clear. Simply we have used this concept of a plus ib into a minus ib is a square minus b square. This concept is used, and in the square root the terms is given, and then also we have multiplied it by the conjugate. So let's move to our fifth question. So moving to our fifth question, the question says convert the following in the polar form. Firstly, what is the polar form? We know that z is equal to x plus iy. So in the polar form, we can write z as r cos theta plus I sin theta. Cos theta plus I sin theta. Here r is the modulus, which is equal to under root of x square plus y square, and theta is the argument. So firstly, whatever expression is given, we will convert it in the standard form. So we are having 1 plus 7i upon a minus b whole square, because 2 minus I square, we can write it as a square plus b square minus 2ab, that is 2 square will be 4, plus b square, that is I square, minus 2ab, that is minus 2 into I. So we are having 1 plus 7i. I square is minus 1. So here we are having 3 minus 4i. But here we can see that I is in the denominator. So in order to remove this, we will multiply it by the conjugate of 3 minus 4i. So 1 plus 7i into 3 plus 4i upon 3 minus 4i into 3 plus 4i. So in the denominator we are having a plus b into a minus b. So a square, that is 3 square, minus b square, that is 4i whole square. And in the numerator we will have 1 into 3 plus 4i, that is 3 plus 4i, plus 7i into 3 plus 4i, that is plus 21i, and 7i into 4i, that is 28i square. So we are having 3 and 28i square will be minus 28, because I square is minus 1, plus 21 plus 4i, that is 25i, and in the denominator we have 9 minus 16i square, and I square is 1, so it will be 9 plus 16. So let's separate this with a line. So we have 3 minus 28, that is equal to minus 25 plus 25i, and in the denominator we have 9 plus 16, that is 25. So we are getting it as 25 minus 25 will get cancelled by 25, so we will left with minus 1 plus I. So this is the standard form. Now we have to express in the polar form like this. So we can write r as under root of x square plus y square. So you can see that here z is equal to x plus iy, that is z is equal to, let's write here, minus 1 plus I, that is x is equal to minus 1 and y is equal to 1. So r is equal to under root of x square plus y square. So it will equal to minus 1 square will be 1 plus y square, 1 square will be plus 1. So r we are getting it as under root of 2. And now theta, here we have to find the argument theta. We have to calculate theta, that is the argument. So we can see that this complex number, first we will see in which quadrant it lies. So we know that in first quadrant both x and y is positive, and in the second quadrant x is negative and y is positive. So it will lie somewhere in the second quadrant. So in the second quadrant we have theta is equal to pi minus alpha. In first quadrant we have alpha, then in second we have pi minus alpha, then in third we have alpha minus pi, and in fourth we have minus alpha. So theta is equal to pi minus alpha, and alpha is equal to tan inverse mod of imaginary part of z upon real part of z. So here we are having alpha is equal to tan inverse imaginary part of z is equal to, here imaginary part of z is 1 upon minus 1. So alpha is equal to tan inverse 1 upon minus 1. So whole modulus is given, so we are having tan inverse 1, and 1 can be written as tan inverse 1 can be written as pi by 4. So tan pi by 4. Now we are getting alpha as, let's separate this with a line. So alpha is equal to tan inverse tan pi by 4. So alpha we are getting pi by 4. Alpha will always be in the acute angle. So we are getting alpha is equal to pi by 4. So theta will be equal to pi minus alpha because it is in the second quadrant. So we are having pi minus pi by 4, which is equal to 3 pi by 4. So in the polar form, we can write z is equal to r. R we are having as under root 2 cos theta. So we are having cos 3 pi by 4 plus I sin theta, that is I sin 3 pi by 4. So this is our desired polar form. This question will not be asked in the exam because polar form is not in the syllabus now, but it is important in respect to the competitive exam. So it is very much important that you learn this because it will be applied in the further exams also. So in the second question, you try to solve this and tell me in the comment if the answer, and if you will not be able to solve, then we will solve in the next video. So I hope this all is clear. In this video, in the fifth question, what we have done, we know that in polar form we can write z as r cos theta plus I sin theta. So firstly we have done this in the standard form. So and then we are getting z in the standard form. Then we calculated r, then alpha, and then we get the argument theta, and then finally we wrote it as z is equal to in the polar form. I hope this video was useful to. Thank you for watching.